All right, let me correct this. I think in the last video I had said we were doing 6 and 7, but it's really 8. It's problem number 8 that we're doing. All right, well, let's get into problem 6 since I've already done 1, 2, and 3 in the other video. All right, so in problem 6 you have two galaxies there. Let's take a look at it. We have a galactic collision taking place. These two similar sized galaxies that have a combined velocity of 1,500 kilometers per second, and if each galaxy is 100 kiloparsecs across, how long does it take these two things to undergo their galactic collision? All right, so the way that we do this is okay. So we could go back to this thing, and here, let me. So the way that we do this, get back to this, here's galaxy A, here's galaxy B. I probably should have put them a little closer together. So they're covering a total distance of 2 times the size of them, right? Each of them are 100 kiloparsecs across, so these are rather large galaxies. All right, anyhow, so 2 times 100 kiloparsecs, and remember the velocity is distance divided by time. If there's no acceleration, which there's not in this case, and they give us the velocity as 1,500 kilometers per second. All right, so we take this equation, right, the velocity is distance divided by time, and we rearrange it and solve for time. So time would be the distance, which of course here's our distance, right, from up here, and I'm just converting that into kilometers. So it's 2 times 100 kilometers per kiloparsecs times the fact that there's 3.1 times 10 to the 16th kilometers in a kiloparsec. So the kiloparsecs will cancel. Okay. And also you divide that by the velocity that's measured. These two things are approaching each other at 1,500 kilometers per second, so the kilometers are going to cancel as well, and so you get 1 over seconds, which of course turn into seconds. So you get, let's see, what did I get? 4.13 times 10 to the 15th seconds. All right, so this is an enormous amount of time. Wouldn't it be nice to figure out how much time this is in years? Okay, so let's go ahead and do that. So for problem, this is just a continuation of problem 6. All right, so we found that the time it takes these two galaxies that are a radius that each have a radius of 100 kiloparsecs. The time is 4.13, and of course they're moving at 1,500 kilometers per second. 4.13 times 10 to the 15th seconds. All right, so of course we're just going to do a conversion between seconds and seconds and years, so that of course there's 60 seconds in one minute. Okay, so I'm not going to write all these, and of course there's 60 minutes in 1 hour. So the hour, the 1 hour goes in the numerator, and then of course there's 24 hours in 1 day, and then finally there's of course approximately 365 days in 1 year. Right, so this would convert it to years if you just simply take this number and divide it by 60, divide it by 60 again, divide it by 24, and then you divide it by 365. All right, so here's what I get when I did this. It turns out to be approximately 1.31, when there's other stuff there, times 10 to the 8th years. All right, so let's look at that. Oops, I don't know what I just drew. Sorry, times. That does not look good at all. Times 10. Sorry about that. Let me erase this. Sorry. All right. Come on, anytime now. All right, this thing doesn't erase very well. All right, so again, times 10 to the 8th years. All right, so let me move the decimal point over 2 places to the right, so that becomes 131 times 10 to the 6th. All right, times 10 to the 6th. Or you could say 131 million years. You could write it like that. 131 million, right? Or mega, either way, million years. All right, so that's how long it takes these two galaxies. All right, remember, we're actually doing number 8 next. All right, so let me clear this so we got some room to do it. All right, and let's go back here and we'll look at number 8. So again, we're not doing 7. I mean, yeah, no, we're not going to do 7. All right, so it says the spectrum of a quasar with a redshift of 0.2 contains 2 sets of absorption lines, and the absorption lines are at 0.15 and 0.155 respectively. All right, if we use H, the usual thing that we use H as 70 kilometers per second per megaparsec. Remember, H is the expansion rate of the universe. Estimate the distance between the intervening galaxy responsible for these 2 sets of lines. Remember, this is that thing we talked about a little bit called the Lyman forest, right? Where that Lyman, the first Lyman line, where the electron makes a transition between the ground state and the first excited state, and so that's, if I remember correctly, that's 122 nanometers, which of course is in the ultraviolet. But of course, since this is a quasar, this thing has crossed a huge fraction of the universe. And so remember, all quasars are at least 10 billion light years away. Well, that was their distance when the light from the quasar left. But see, in between, it passed this galaxy, all right, or something. I mean, it could have just been a cold cloud, but more than likely it was a galaxy that absorbed the energy at this rate. And so what we can do is now we can figure out the distance to that the galaxy in between. Okay, so here's this is number 8. All right, so here's the quasar. All right, so I don't know. This is our quasar, and it's it's emitting light. That's supposed to be the light. And so what happens, of course, is as the universe expands, the light, the wavelength gets bigger and bigger. All right, so and then what happened is in between on the way to the Earth, over the light gets absorbed, and so let's say there's some intermediate galaxy or something like that. It could be a galaxy, it could just be gas and dust that's between the galaxies. Anyhow, the light gets absorbed, and so that absorption rate, they give us what that is, and let's see, they give us the red shifts. All right, so what equation could we use here? So it's really this. It's really the Hubble's law. The distance is always equal to the velocity. The recession velocity divided by, of course, the Hubble constant, which is always 70. That's what we generally use. But in this particular case, the velocity here. So they're giving us the redshift. And so it's really it's what it's really going to be is redshift. So I'm going to call that redshift 2, the second one, minus redshift 1. All right, remember, like in the problem, they tell us, respectively. So, the first number they gave us is redshift 1. The second number they gave us is redshift 2. Anyhow, those are just pure numbers. But if we multiply those by the speed of light, right, that fraction is going to give us the recession velocity. All right. Anyhow, you divide that by Hubble's the Hubble constant. All right. So this is exactly the same thing. The numerator here, this is just a number minus another number. But remember, that's the redshift. And so just as a reminder, let me do it over here. The redshift is a reflection of the velocity divided by the speed of light. See, so this basically the speed of light. The units would work out correctly. All right. So anyhow, this is what the R's are equal to, but we're just given the numbers. All right. So anyhow, I've already talked about this too much. So the distance here is going to equal. All right. So let's see. Our second redshift was 0.155. All right. So that's redshift 2. So I'm going to put this in parentheses, 0.155. Remember, this is just a number, minus, what that number is, of course, is the speed of light divided by, the speed, the speed that the Doppler shift is giving us divided by the speed of light. Anyhow, to minus the first redshift, which is 0.15. All right, so that's, just a tiny little amount. And then in this particular case, let's represent the speed of light as, as kilometers per second, because remember, in the Hubble constant, it's in kilometers per second per megaparsec. All right, so the speed of light is 3 times 10 to the 5th, all right, 10 to the 5th kilometers per second, divided by 70 kilometers per second, 70 kilometers per second per megaparsec. All right, and so of course, megaparsec. Of course, that's supposed to be a P. The kilometers per second in the numerator and denominator cancel each other, and this whole thing comes out to be basically 1,500 divided by 70, or 21.4 megaparsecs. So that's what this comes out to be. All right, let's see if I have room here. 21.4 megaparsecs. All right, so here, let me write that in a little bit. So you just subtract these two numbers, multiply it by the speed of light in kilometers per second, divide it by the Hubble constant, and the units are, of course, in megaparsecs, because 1 over megaparsecs, the megaparsecs come up to the numerator. So the distance to the galaxy that's in between, so the distance here, this is number 8. I know I just wrote it, but it was kind of scrunched up, so I want to write it again. Turns out to be 21.4 megaparsecs. All right, so that's how we know how far the stuff in between is, right? So you have, here's the quasar really far away, and then the light is coming from it, and then it encounters a galaxy. On one side, you get this the first redshift, and then the second redshift, and then you're really figuring out what this distance is here, the distance between this intermediate galaxy and the Earth, right, or really the Sun. All right, and so that's what it turns out to be for this particular problem. All right, 21.4 megaparsecs. All right, very good. So that's it for these problems from chapter 25. All right.